Section 1 of the Chemical Constituents of the Active Principle of the Ava Root by Alice A. Ball. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Thesis presented for the degree of Master of Science at the College of Hawaii, June 1915, by Alice A. Ball. The thesis herewith on the chemical constituents of the active principle of the Ava root by Alice A. Ball clearly demonstrates her ability to do original work and to present her results in logical form. Approved. J. F. Illingworth, Chair of the Committee on Advanced Degrees, College of Hawaii, May 14, 1915. The chemical constituents of Piper Methysticum, or the chemical constituents of the active principle of the Ava root. Historical. Among the customs peculiar to the inhabitants of the South Pacific Islands, perhaps the most noted is that of the preparation and drinking of a narcotic beverage called ava, kava, or yakona. Much of its notoriety arises from the repulsive way in which it is sometimes made. Aside from this, it is characteristic of a certain oceanic area and seems to be as strikingly limited to this area as is the stick and groove method of making fire. The custom is not confined to one ethnic stock, many notices in literature showing that both Papuans and Polynesians practice it. In many of the islands, the liquor is concocted by chewing the root of the Macropiper methysticum, or long pepper, ejecting the comminuted mass into a bowl, adding water, straining out the pulp, and drinking the fluid. In other localities, it is made by simply grating the root and adding water. The plant from which the kava is made is a shrub of the natural order Piperaceae. It is about 6 feet high, with stems ranging from 1 inch to 1.5 inches in thickness. The leaves are cordate and from 4 to 8 inches long. This family is the source of the pepper of commerce and contains several species that are of medicinal and commercial importance. In making kava, the root and base of the stem is used. The roots usually weigh from 2 to 4 pounds, though sometimes as much as 22 pounds. Several varieties are distinguished by the natives. For instance, in Tahiti, there is a yellow variety called Maria. Another, which becomes pink on exposure to the air, is called Avini Ute. Chewed when freshly gathered, the root first tastes sweet and aromatic, then bitter, acrid, and pungent. It provokes abundant secretion of saliva and in a few seconds occasions a sensation of burning on the tongue. The root contains about 50% of starch, a little pale yellow essential oil, 2% of an acrid resin, and 1% of the neutral crystalline principle, Methysticin, called kavahine. To the latter principle we must attribute the toxic qualities of the kava preparation. The resin and the kavahine are insoluble in water, but are soluble in saliva and the gastric juices. In Samoa, the ava root is grated or chewed, then soaked, the woody pulp strained off, and the fluid drunk. The root is used either dry or green. The flavor of the liquid is at first like that of soapsuds, but immediately afterward a pleasant aromatic taste is imparted, faintly bitter, as in quinine. In Samoa, ava drinking is the accompaniment of all meetings of the men. Kava is at first stimulating, but the effect of an excess resembles that of opium, producing a drowsy drunkenness, lasting for 2 hours. The inebriate is usually peaceable, but sometimes is irritated by noises, which is attributed by natives to the use of kava grown in moist ground. The results of excess are skin disease, emaciation, and general decrepitude. The peculiar whiteness of the skin caused by kava drinking is said to be sought after in some islands as a sign that its possessor is wealthy enough to devote his time to its acquirement. There is some misapprehension in regard to whether the liquid undergoes fermentation before it is consumed, but it is positively known that there can be no fermentation, for the liquor is drunk immediately after the addition of water to the macerated root. Kava that is prepared by chewing is said to be more palatable, which is perhaps due to the conversion of the starch into a fermentable substance by the ptyalin of the saliva. In 1779, Captain King, R.N., who followed Captain Cook to the islands, describes the case of a priest as follows, quote, "A little old man of an emaciated figure, his eyes exceedingly sore and red, and his body covered with a white leprous scurf, the effects of an immoderate use of ava." Unquote. He also says, quote, "The chiefs suffer dreadful effects from the immoderate use of ava. Those who are most affected by it had their bodies covered with a white scurf, their eyes red and inflamed, their limbs emaciated, their whole frame trembling and accompanied with a disability to raise the head." Unquote. F.A. Greele makes the following statement in a footnote, quote, "The mixture is a subnarcotic, and if drunk by European sailors, produces highly nauseous effects. If frequently taken, a dry burning heat is produced all over the body, the eyes become red, skin peels off in flakes, and then degenerates into leprous ulcers, or the whole body becomes emaciated and wastes away." Unquote. Numerous attempts have been made to isolate the active chemical constituent or constituents. As early as 1844, Morson discovered an active principle, kawine. This is a greenish-yellow, strongly aromatic and acrid resin. This was again studied by Coussant in 1860. Gobley isolated from kava root a crystalline principle analogous to piperin, methysticin, or kavaine, which is without odor and taste and is probably inert. In 1886, Lewin separated the resin into two resins, of which the beta resin is greasy and of a reddish-brown color, appearing in mass almost black. This is less active than the alpha resin, which is yellowish-brown, has the characteristic odor of the drug, is freely soluble in alcohol, and placed upon the tongue produces a burning sensation followed by local anesthesia. A volatile oil has been found in the root. Laveille claimed to have obtained an alkaloid, kavaine. The following statement was found in Watt's Chemical Dictionary: kawaine, a crystalline resin occurring along with methysticin in kawa. It is not a glucoside. On oxidation, it yields benzoic acid. The following statement appears in the Encyclopaedia Britannica, quote, "There appears to be little doubt that the active principle in this beverage is a poison of an alkaloidal nature. It seems likely that this substance is not present as such, that is, as a free alkaloid in the plant, but that it exists in the form of a glucoside, and that by the process of chewing, this glucoside is split up by one of the ferments in the saliva, and the free alkaloid and sugar is formed." Unquote. Arthur Bossingham communicates the results of a chemical examination of kava. Besides the crystalline body, methysticin, which has already been described by others, he was able to isolate and identify three resins: one soluble in 5% solution of potassium carbonate, the second insoluble in this, but soluble in 5% solution of caustic potash, while the third was insoluble in both of these alkaline solvents. The ash amounts to 2.495% of the air-dried root and contained, besides mere traces of iron, manganese, mainly calcium, sodium, and potassium. End of section 1. Section 2 of the Chemical Constituents of the Active Principle of the Ava Root by Alice A. Ball. This LibriVox recording is in the public domain. Method of extraction. The fresh rhizome was chopped up and then ground up by means of a meat chopper. In the preliminary work, the material was dried in a vacuum oven at a temperature not exceeding 40 degrees centigrade. In the later work, the material was rapidly dried in the sun. This operation required about 2 days' time. After being thoroughly dried, the material was finely powdered and then extracted with ether. The following continuous extraction apparatus was used. Due to the extreme rapidity with which the ether evaporated, it was necessary to surround the coils with ice so as to keep the condensers cold. Method of separation of the resins. After the removal of the crystalline methysticin from the extract, the following method of separation of the resinous products was used. The free acids were removed by shaking the total resin successively with solutions of 1% ammonium carbonate, 1% sodium carbonate, and 1% sodium hydroxide. The acids thus removed were recovered by treating the alkaline solution with dilute hydrochloric acid and shaking out with ether. The three acids were not markedly different in their physical properties. They possessed the characteristic odor of the crude drug, were viscous, brown in color, and did not solidify at -10 degrees centigrade. These free acids constitute about 5% of the total resins. The remainder of the extract was treated with alcoholic potassium hydroxide and saponified by heating the solution to about 80 degrees for 15 minutes. After the alcohol was removed by distillation, a small quantity of water was added. This resulting solution was then extracted with ether to remove the alcohol radical or radicals and the unsaponifiable material from the saponified product. The ether extract was saved to be used in the work on the alcohol radicals. The aqueous portion was evaporated to a semi-solid mass. Carbon dioxide was passed over this mass for about 15 minutes to change any excess of potassium hydroxide to potassium carbonate. Alcohol, 95%, was then added to precipitate the carbonate. The carbonate was then filtered off and water added to the filtrate. To the clear filtrate, a solution of barium chloride was added. Immediately, a dense, thick, cream-yellow precipitate formed. Barium chloride was added in excess. The barium salt was filtered off by means of a suction pump, and the precipitate washed with water. The filtrate was treated with a few drops more of barium chloride so as to be sure that an excess had been added, which was proven if no further precipitate formed. To this clear filtrate, an excess of a solution of ferric chloride was added. Immediately, a thick, heavy precipitate of the iron salt came down, which was filtered off by means of a suction pump, and the precipitate washed with water. The barium precipitate was treated with dilute hydrochloric acid and heated to boiling to decompose the barium resinate and to liberate the free resin acid. The liberated acid was a brown resin of a thin consistency and had a characteristic odor. This acid was removed by shaking out with ether. The ethereal solution was dried with anhydrous sodium sulfate, filtered, and the ether removed by distillation. The last traces of ether were removed by heating the resin acids in a vacuum oven at 65 degrees centigrade. This resinous acid is the acid spoken hereafter in this paper as the barium acid. The iron precipitate was treated with dilute sulfuric acid, ferric chloride is soluble in ether, and ferric sulfate is not, and heated to boiling to decompose the iron resinate. The acid, when liberated, had a strong, characteristic aromatic odor. It was extracted with ether in the same manner as the barium acid. This resinous acid is the acid spoken of in this paper as the iron acid. The resinous extract left after the removal of the crystalline methysticin is spoken of as the total resins. The resin acids removed by the preliminary shaking out with the various aqueous alkalis are spoken of as the total free acids. The various metallic salts of the resinous acids. After obtaining the potassium salts of the acids and having freed the same from the excess of the potassium hydroxide and potassium carbonate, the possibilities of the formation of different metallic salts were tried. The soluble salts of the following metals yielded precipitates: manganese, barium, cobalt, silver, mercury, iron, zinc, copper, calcium, lead. The following metallic salts gave a complete precipitation: silver, iron, ferric, manganese. Since the barium and iron ferric salts gave the best means of separation, they were used to separate the resins. The total resins. The total resins were brown in color, thick, syrupy consistency, and possessed the characteristic odor of the drug. A molecular weight determination was made in the same manner as with the barium acids, and the following data obtained. Weight of pipette before, 18.7660. Weight of pipette after, 14.7160. Weight of resin used, 4.0500. Temperature before, 3.52. Temperature after, 3.71. Change in temperature, 0.18. Volume, 37 cc. Constant for solvent, 3,280. Approximate molecular weight, 2,000. Combustions were made and the following data obtained. Weight of boat, 3.4722, 3.4720. Weight of boat and resin, 3.6355, 3.6220. Weight of resin, 0.1633, 0.1500. Sulfuric acid tube, 79.1051, 79.3865. Tube plus water, 79.2073, 79.4770. Water, 0.1022, 0.0905. Hydrogen equivalent, 0.01136, 0.01006. Potassium hydroxide bulb, 49.4316, 50.8720. Bulb plus carbon dioxide, 49.8350, 51.2430. Carbon dioxide, 0.4034, 0.3710. Carbon equivalent, 0.12102, 0.1010. Percent carbon, 67.31%, 67.3%. Percent hydrogen, 6.9%, 6.7%. Percent oxygen, 26.8%, 27.0%. The total resins, when placed on the end of the tongue, produced a marked stinging sensation followed by a local anesthesia. After the first stinging was produced, the sensation was rather pleasant. The local anesthesia persisted a long time, giving a sensation much the same as that produced by cocaine. The barium and iron acids also produced this local anesthesia, but the initial stinging sensation was much more pronounced, which was probably due to the acid nature of the substance. End of section 2. Section 3 of The Chemical Constituents of the Active Principle of the Ava Root by Alice A. Ball. This LibriVox recording is in the public domain. The barium acid. The resinous material used and spoken of as the barium acid is the material prepared and so named as given under the method of separation. Physical properties. Dark reddish-brown in color, syrupy in consistency, and has a characteristic odor. Heavier than water, soluble in benzol, ether, alcohol, and acetone, but insoluble in petroleum ether and water. This resin constitutes about 60% of the total ester resins, that is, the resins left after the free acids have been removed with aqueous potassium hydroxide. An analysis of the barium salt obtained by precipitation from the potassium soap was made, and the following data obtained. Weight of substance used, 1.1715. Weight of barium sulfate, 0.4430. Barium equivalent, 0.2606. Percent barium, 22.2%. Weight of substance used, 0.5860. Weight of barium sulfate, 0.2205. Barium equivalent, 0.1298. Percent barium, 22.1%. The following method was used in making the above analysis. The weighed material was ignited in a platinum crucible by gently heating until the combustible gases formed were given off. The crucible was then more strongly heated to completely burn off the carbonaceous material left. The residue was extracted with nitric acid, and the barium precipitated as the sulfate with dilute sulfuric acid, and the weight of the barium sulfate determined. Expressed as acid number, or the number of milligrams of potassium hydroxide required to neutralize the free acids in 1 gram of the substance, the following data was obtained. Barium equivalent, 0.2606. Barium expressed as KOH equivalent, 0.2131. Weight of material used, 1.1715. Milligrams of KOH per gram, 181.9. Acid number, 181.9. Barium equivalent, 0.1298. Barium expressed as KOH equivalent, 0.1062. Weight of material used, 0.5860. Milligrams of KOH per gram, 181.3. Acid number, 181.3. The following gives the acid number obtained by direct titration of the barium acid. In A, barium hydroxide was used, and in B, sodium hydroxide was used. A small quantity of the material was dissolved in a sufficient quantity of neutralized alcohol to give a liquid of a light yellow color. Phenolphthalein was used as the indicator, and the alkali was added until a red color was produced. Weight of substance, A, 0.6160, B, 0.2345. cc of alkali, A, 4.54, B, 1.75. KOH equivalent per gram, A, 41.40, B, 41.90. Acid number, A, 41.40, B, 41.90. On evaporating a portion of the alcohol from the material left after titrating with the sodium hydroxide, and adding water to obtain an aqueous solution of the sodium salt, an emulsion was formed, and on standing, globules of the free resinous acid separated. From the data thus obtained, it can readily be seen that the acid or acids which constitute the barium acid must have a number of carboxyl groups and form a different series of salts by precipitation than by direct titration. The salt or salts formed by direct titration, although neutral to phenolphthalein, may be acid in structure. This is further shown by the fact that the potassium salts produced by direct titration are readily hydrolyzed. The acid number obtained by the precipitation of the barium salt may be called the combining value, and the acid number obtained by titration, the titration value. A number of molecular weight determinations were made on the free barium acid. McCoy's boiling point apparatus was used, and Merck's benzol, free from thiophene, was used as the solvent. A weighing pipette with a bulb was used to introduce the material, the bulb being weighed before the material was introduced into the apparatus and afterwards, the difference being the weight of the material used. Weight of pipette before, 16.3670. Weight of pipette after, 14.8895. Weight of material used, 1.5225. Original temperature, 3.53. Final temperature, 3.60. Change in temperature, 0.07. Volume of solution, 37 cc. Constant for solvent, 3,280. Approximate molecular weight, 2,000. Weight of pipette before, 14.8895. Weight of pipette after, 12.4610. Weight of material used, 2.4285. Original temperature, 3.53. Final temperature, 3.62 to 3. Change in temperature, 0.09. Volume of solution, 43.5 cc. Constant for solvent, 3,280. Approximate molecular weight, 2,100 or 1,800. Combustions were made using the barium acids. By qualitative tests, it was found that the acids contain only carbon, hydrogen, and oxygen. The following gives the results of the combustions. Weight of boat, 2.8402. Weight of boat and resin, 3.0500. Weight of resin, 0.2098. Weight of H2SO4 tube, 78.0250. Weight of tube plus water, 78.1520. Weight of water, 0.1270. Hydrogen equivalent, 0.0143. Weight of KOH bulb, 48.8140. Weight of bulb plus CO2, 49.3800. Weight of CO2, 0.5660. Carbon equivalent, 0.1543. Percent hydrogen, 78.5%. Percent carbon, 6.8%. Percent oxygen, 19.7%. Weight of boat, 2.8402. Weight of boat and resin, 3.0250. Weight of resin, 0.1848. Weight of H2SO4 tube, 78.1415. Weight of tube plus water, 78.2550. Weight of water, 0.1135. Hydrogen equivalent, 0.126. Weight of KOH bulb, 51.7095. Weight of bulb plus CO2, 52.2085. Weight of CO2, 0.4990. Carbon equivalent, 0.1361. Percent hydrogen, 73.6%. Percent carbon, 6.8%. Percent oxygen, 19.6%. An attempt was made to make the potassium salts of the barium acids by saponification with alcoholic potash. A small quantity of the acid was treated with an excess of 10% alcoholic potash and heated to 80 degrees centigrade to complete the saponification. Instead of the formation of the potassium salts, a thick, dark brown, solid gummy mass separated. On cooling, it solidified to a brittle solid which had all the physical properties of a true resin. This solid is soluble in ether, chloroform, and benzol, slightly soluble in alcohol, and insoluble in petroleum ether and water. It burns without the formation of an ash. Evidently, this brittle material is a condensation product of the original barium acid. End of section 3. Section 4 of the Chemical Constituents of the Active Principle of the Arrowroot by Alice A. Ball. This LibriVox recording is in the public domain. Oxidation products of the barium acids. A small amount of the barium acids was sealed with concentrated nitric acid in a hard glass tube and heated in a bomb furnace for an hour and a half at 115 to 120 degrees centigrade. On cooling, a yellow solid separated. Qualitative tests showed that this oxidation product contained no nitrogen, combined with sodium hydroxide readily, is soluble in hot water, slightly soluble in cold water, easily soluble in ether, alcohol, and benzol, and slightly soluble in carbon tetrachloride. It decolorizes alkaline permanganate, but does not decolorize bromine water. That there are a number of intermediate products formed and that nitration also takes place during the formation of these intermediate products is shown by the following. A small quantity of the acids were placed in a test tube and covered with concentrated nitric acid. This was suspended in an H2SO4 bath and a thermometer inserted so as to observe the temperature. On being gently warmed, the nitric acid and the resin began to react with a rapid evolution of carbon dioxide and oxides of nitrogen. As soon as the reaction had modified, and before the temperature rose above 100 degrees centigrade, a small amount was removed and added to water. Some of the solid acid was formed and also a number of globules of oil, and there was a strong persistent odor of nitrobenzene. The original test tube was heated to about 120 degrees centigrade and a small portion again removed. There was more of the solid material formed, and the odor was similar to vanillin or coumarin or cinnamic aldehyde. The test tube was again tested when the temperature had reached 135 degrees centigrade. There was no aromatic odor and a large amount of the solid formed. When viewed under the microscope, the substance had the appearance of curled threads. When the barium acids were treated with the standard nitrating mixture, a solid was obtained which showed the presence of nitrogen when the standard test was applied. After the preliminary tests were made, the following method of preparation was used. 2 or 3 grams of the barium acids were introduced into a hard glass tube of about 30 centimeters in length and 15 or 20 cubic centimeters of concentrated nitric acid added. The reaction, which is very vigorous at first, was regulated by keeping the tube under running water. After this vigorous action was over, the tube was placed in a sulfuric acid bath, and the temperature gradually increased until it had reached 125 degrees centigrade, at which temperature it was kept for about 5 hours. It was necessary to add small quantities of nitric acid from time to make up the loss by evaporation. When the oxidation was completed, the product was poured into water and then heated to boiling. The resulting solution was filtered and the filtrate allowed to cool. On standing, a quantity of pale yellow substance separated. The following data gives the percent yield of this oxidation product. Weight of container, 6.7220. Weight of container and substance, 7.5920. Weight of substance, 0.8700. Weight of oxidation product, 0.1240. Percent yield, 14%. The oxidation product was dried by placing it in a vacuum over sulfuric acid for several days. The neutralization equivalent of this crude oxidation product was 157. Weight of substance used, 0.0502. Number cc of 10th normal sodium hydroxide, 3.2 cc. Neutralization equivalent, 157. The oxidation product was heated on a watch crystal and the sublimate allowed to collect on a funnel. The first sublimate gave a melting point of 109 degrees centigrade. Combustions were made on this sublimate with the following results. 1. Carbon 66%, hydrogen 4.7%. 2. Carbon 65.7%, hydrogen 4.8%. 3. Carbon 65.15%, hydrogen 4.8%. 4. Carbon 65.8%, hydrogen 4.85%. The neutralization equivalent was obtained by titrating an alcoholic solution of the sublimate with standard sodium hydroxide. The following results were obtained on 2 different lots of the sublimed oxidation product. Weight of substance, 0.09. cc of alkali N/10, 7 cc. Neutralization equivalent, 128.6. Weight of substance, 0.1006. cc of alkali N/10, 7.9 cc. Neutralization equivalent, 127.3. Using a third sample, the neutralization equivalent was obtained from the analysis of the silver salt. The silver salt was formed by adding silver nitrate solution to a carefully neutralized solution of the sublimate. The insoluble silver salt was filtered off, washed with water to remove the excess of silver nitrate, and dried in a vacuum over sulfuric acid for several days. A weighed quantity of the silver salt was ignited in a platinum crucible, and the residue of metallic silver was weighed. The following data were obtained using material from the same sample for each analysis. Weight of dish, 12.8825. Weight of dish and substance, 13.0060. Weight of substance, 0.1235. Weight of dish and silver, 12.9400. Weight of silver, 0.0575. Neutralization equivalent, 125. Weight of dish, 12.8826. Weight of dish and substance, 13.1310. Weight of substance, 0.2484. Weight of dish and silver, 12.9980. Weight of silver, 0.1154. Neutralization equivalent, 125.3. Using the same sample, a neutralization equivalent was obtained by titration with standard sodium hydroxide. Weight of substance, 0.0912. 10th normal sodium hydroxide, 7.25 cc. Neutralization equivalent, 125.8. The above data shows that the sublimate is a mixture. No empirical formula can be calculated from the combustions, and different samples give different neutralization equivalents, although the duplicate determinations on the same sample showed good agreement, thus demonstrating the reliability of the methods. By fractional sublimation, it was possible to obtain fractions with different melting points. The first sublimate melted sharply at 109 degrees. From the last fraction, it was possible to separate some crystals that melt at 200 degrees centigrade. These might possibly be para-acetyl benzoic acid, as its properties of solubility, crystalline form, its melting point, and power of sublimation agree with those of para-acetyl benzoic acid. Those crystals that appeared identical with benzoic acid were placed in a melting point tube, and some known benzoic acid from toluol was placed in another tube. These two tubes were placed in the same sulfuric acid container and their melting points taken at the same time. They melted at the same temperature. The sublimate had a very pleasant aromatic odor resembling benzoin. It gave no coloration with ferric chloride, thus eliminating a large group of aromatic compounds. Some of the crystals were found to be identical with benzoic acid when examined under the microscope. The characteristic odor of methyl benzoate was produced when a small quantity of the crystals were heated with methyl alcohol and concentrated sulfuric acid. On treating some of the carefully neutralized product with ferric chloride solution, a flesh-colored precipitate was formed. It agreed closely in its analysis with the precipitate formed with known benzoic acid. The filtrate left after the removal of the iron precipitate was acidified and extracted with ether, and the ether removed by evaporation. The resulting substance decolorized alkaline permanganate solution, but did not decolorize bromine water. When the leaflet needles that melt at 200 degrees were mechanically removed from the original sublimate, the substance left after precipitating with ferric chloride melted at 109 degrees. When these crystals were not removed, the melting point of this material was not definite, but was over a range of 5 degrees, from 110 to 115 degrees centigrade. The oxidation product contains at least 3 distinct substances: benzoic acid, a substance melting at 200 degrees and which is probably para-acetyl benzoic acid, and a third substance melting at 110 degrees. End of section 4. Section 5 of the Chemical Constituents of the Ava Root by Alice A. Ball. This LibriVox recording is in the public domain. The iron acids. The resinous material used and spoken of as the iron acids is the material prepared and so named under the method of separation. Physical properties. Transparent and reddish-brown in color, oily in consistency, and has a characteristic tea-like odor, heavier than water, freely soluble in benzol, ether, alcohol, and acetone, but insoluble in petroleum ether and water. This resin constitutes about 18% of the total ester resins. By qualitative tests, it was shown that the acids contained only carbon, hydrogen, and oxygen. Combustions made on the iron acids gave the following results. Weight of boat 2.6950 and 2.6950. Weight of boat and substance 2.8470 and 2.8495. Weight of substance 0.1520 and 0.1545. Potassium hydroxide bulb 50.9620 and 51.0805. Bulb and carbon dioxide 51.3370 and 51.4610. Weight of carbon dioxide 0.3750 and 0.3805. Carbon equivalent 0.1023 and 0.10376. Sulfuric acid tube 76.2448 and 76.3450. Tube and water 76.3400 and 76.4453. Weight of water 0.0952 and 0.1003. Hydrogen equivalents 0.0106 and 0.01114. Percent carbon 67.3% and 67.2%. Percent hydrogen 7.0% and 7.2%. Percent oxygen 25.7% and 25.6%. An analysis of the iron salt obtained by precipitation from the potassium soap gave the following data. Weight of substance used 0.2955 and 0.3387. Weight of ferric sulfate 0.0445 and 0.0509. Ferric equivalents 0.03208 and 0.03676. Percent iron 10.85% and 10.85%. The following method was used in making the above analysis. The weighed material was ignited in a platinum crucible by gently heating until the combustible gases formed were given off. The crucible was then strongly heated until the carbonaceous material was completely burned off. The residue was weighed and the percentage of iron determined. Expressed as the acid number or the number of milligrams of KOH required to neutralize the free acids in 1 gram of the substance, the following data was obtained. Ferric equivalent 0.03208 and 0.03676. Iron expressed as KOH equivalents 0.0965 and 0.1107. Weight of material used 0.2955 and 0.3387. Milligrams of KOH per gram 326.6 and 326.7. Acid number 326.6 and 326.7. The following gives the acid number obtained by direct titration of the iron acid. The method is the same as that used in getting the titration value of the barium acid. Weight of substance 0.2450 and 0.2472. cc of alkali 2.2 and 2.3. KOH equivalents 0.01232 and 0.01288. Potassium hydroxide equivalents per gram 53.87 and 52. An attempt was made to saponify some of the iron acid, but it was impossible. The alcohol was partially distilled off, and the acid freed by making the mass acid with sulfuric acid and shaking out with ether. The ether was distilled off, but the remaining acid had different physical properties from the acid with which the experiment was started. It was lighter in color and solidified at 0 degrees. At room temperature, it was almost solid. On ignition, it left no ash. This probably is a polymerization product of the original acid. Since many organic acids whose salts cannot be prepared by the ordinary methods can be prepared by passing dry ammonia gas through a solution of the acid in anhydrous ether, this method was tried with the iron acid. The iron acid was dissolved in anhydrous ether, and the dry ammonia gas was bubbled through this ether solution. At first, no change was noted, but after several minutes there was a flocculent, thready precipitate formed, which was light brown in color. The experiment was repeated. At first the precipitate was a very light brown, but after forming it quickly darkened. After standing a few hours, the flocculent precipitate changed to a sticky brown mass. This same change was produced immediately if the precipitate was exposed to the air. The resulting mass had no odor of ammonia. The flocculent precipitate formed at first was probably the ammonium salt of the iron acid, which, like most ammonium salts, it was precipitated due to its insolubility in ether. Due to the ease of hydrolysis, this salt immediately decomposed to the acid and ammonia when traces of moisture were present. Oxidation of the iron acids and the free acids. When the iron acids were oxidized in the same manner as the barium acids, the amount of the oxidation product formed was about 1/4 of that produced with an equal amount of the barium acids. The time necessary to completely oxidize the iron acids was much less than required for the barium acids. On sublimation, the iron acid gave a product melting at 110 degrees centigrade and is probably identical with the one formed from the barium acids. The iron acid also yielded a sublimate melting at 200 degrees centigrade. The free acids, when oxidized in a like manner, gave as one of the products a low-melting crystalline compound that contained nitrogen. The iron acid, although related to the barium acid as shown by the formation of a common oxidation product, is different in structure, as shown by the difference in the amount of the oxidation product formed and the time to complete the oxidation. End of section 5. Section 6 of The Chemical Constituents of the Active Principle of the Ava Root by Alice A. Ball. This LibriVox recording is in the public domain. The alcohol radicals and unsaponifiable material. The material that was shaken out with ether after the saponification consists of the unsaponifiable material and the alcohol radicals of the acids produced by saponification. On allowing the ether to evaporate from this material, feathery needles separated. These were removed by means of a suction pump and recrystallized from hot acetone. The melting point of this product was 122 to 125 degrees centigrade. The precipitate was dissolved in benzol and allowed to slowly crystallize. It formed long prismatic needles with melting point of 130 degrees centigrade. When heated with concentrated sulfuric acid, a brown-green fluorescent solution was produced. The remaining material was steam distilled and the distillate extracted with ether to remove the oil. The ether was dried with anhydrous sodium carbonate, the solution filtered, and the ether removed by distillation. The oil that remained was light yellow, specific gravity less than that of water, and possessed a very characteristic odor resembling that of musk. The material left after the steam distillation was cooled and shaken out with ether. The ethereal solution was dried with anhydrous sodium sulfate, and the ether removed by distillation. The resulting mass was a dark brown resin without any characteristic odor, solidifying at 0 degrees. The crystalline product with a melting point of 130 degrees and the essential oil are evidently the alcohols formed through saponification of the resin esters. The crystalline product could be readily separated from the resinous material because of its slight solubility in acetone. Since this product was not precipitated when the unsaponified resin esters were treated with acetone, and because it did not make its appearance until after the process of saponification, it is quite probable it is a product of saponification. The essential oil can be detected in extremely small amounts due to its penetrating, characteristic odor. Before the process of saponification, it could not be detected, but as soon as saponification took place, the odor was very marked. From this, it is quite evident that this oil is a product of saponification. The dark brown resinous mass that remained may be either an alcoholic resin formed through the hydrolysis of the ester resins, or it may be a resin belonging to the class known as resins, which resist saponification. Methysticin and methysticinic acid. The crystalline product obtained from the ether extract was recrystallized several times from absolute alcohol to remove all traces of any resinous material. It had a melting point of 122 to 123. It therefore was not pure methysticin, which has a melting point of 138 to 139 degrees. On examining this product under the microscope, it was found to contain two distinct forms of crystals, long needles and prismatic plates. Some free methysticinic acid, melting point 180, was examined under the microscope and found to consist entirely of prismatic plates. Therefore, the original crystalline body contains some methysticinic acid. Some of the original precipitate was crystallized once from absolute alcohol and thoroughly dried. This was used for the following data to determine the percent of free methysticinic acid in the crystalline product. A weighed amount of the crystalline product was dissolved in carefully neutralized alcohol and titrated with 10th normal sodium hydroxide using phenolphthalein as the indicator. Weight of substance used, 0.2590. 10th normal sodium hydroxide, 0.5 cc, percent methysticinic acid. The potassium salts of the various resin acids formed by the saponification of the ester resins should yield a resinous mass, syrupy or oily in consistency when acidified, if it consists entirely of the two groups of acids spoken of as the iron acids and the barium acids. Also, the weight of the barium acids plus the weight of the iron acids should nearly equal the weight of the ester resins, if these are the only two acids, because the alcohol radicals constitute not more than 2% of the ester resins. But when the total potassium salts were acidified, the product formed contained a crystalline substance in addition to the resinous acids. This crystalline substance was separated from the resinous acids by means of their difference in solubility in ether. On recrystallization from absolute alcohol, it had a melting point of 179 degrees centigrade. It is therefore methysticinic acid. This acid constitutes about 20% of the total acids from the ester resins because the barium and iron acids constitute only about 75%. This methysticinic acid cannot be entirely formed by hydrolysis of methysticin, which was incompletely removed from the resinous material. The methysticinic acid existed either combined with some other alcohol than methyl alcohol or was combined with one of the resin alcohol radicals. End of section 6. Section 7 of the Chemical Constituents of the Active Principle of the Ava Root by Alice A. Ball. This LibriVox recording is in the public domain. Physiological action. Due to the impossibility of preparing the alkali salts of the barium and iron acids so as to be positive that the resulting preparations completely represented the barium and iron acids, and due to the insolubility of the acids and the total resins in solvents from which they would not again be precipitated when introduced into the circulation, it was found necessary to make an emulsion. The emulsifying agent used was acacia gum arabic. It was possible by careful preparation to make a permanent emulsion that was miscible with water in all proportions to form a homogeneous mixture. The animals used were rabbits of about 6 pounds weight. The injections were made by Dr. George McCoy, director of the Leprosy Investigation Station at Kalihi. All the physiological experiments were made at the Bacteriological Laboratory at the Leprosy Investigation Station. 1 cubic centimeter of the emulsion of the total resinous extract, strength 1 in 5, was injected into the ear of a rabbit. The animal died immediately. Another rabbit was injected in the same manner with 1/2 cubic centimeter of the same preparation. The animal immediately stretched out and became rigid or appeared to be paralyzed. But after several minutes, these symptoms lessened, and after about 5 minutes, the rabbit appeared normal as far as activity was concerned. As soon as the rabbit had recovered, a second injection of 1/4 of a cubic centimeter of the same preparation was injected in the same manner into the same animal. The same symptoms were produced, and with equal intensity, but 10 minutes passed before the animal again became conscious. For several minutes after recovery, the animal appeared somewhat drowsy and stupid, but it soon regained its former activity. 1/2 cubic centimeter of the iron acid emulsion, strength 1:7, was injected into the ear of a rabbit. Immediate paralysis and apparent anesthesia set in, lasting very pronouncedly for 8 minutes. The rabbit's head was drawn backwards and its legs stiffened, giving symptoms similar to strychnine poisoning, but they did not persist. When a second injection of 1/4 cubic centimeter was given to the same animal, the same symptoms were produced, the animal remaining under the influence of the injection for about 15 minutes. The iron acid injection was repeated on another rabbit with the same pronounced symptoms of strychnine poisoning, but the effect lasted only about 10 minutes. 1/2 cubic centimeter of the barium acid emulsion, strength 1:7, was injected into the ear vein of a rabbit. The animal uttered several loud cries, and after moving several feet, it became spastic and went into a sort of stupor, beginning to come out of it after 10 minutes. As soon as the animal recovered, a second injection of 1/4 cubic centimeter was made. The animal again uttered loud cries, and then it went into a stupor, but it was not spastic. This lasted approximately 10 minutes. The animal did not completely recover until about 20 minutes. Thinking that the action might be largely mechanical and that the symptoms produced were from the emulsion itself and not from the effect of the material that was emulsified, an emulsion of olive oil was used in a like manner. This olive oil emulsion was made in approximately the same consistency as the resinous emulsions, and 1 cubic centimeter was injected into the ear vein of a rabbit. No visible effects followed this injection during the 1 hour's time the rabbit was under observation. 1 cubic centimeter intraperitoneal injections of the total resinous extract emulsion and the same amount of the iron acid emulsion were made into rabbits. During the 3 hours the animals were under observation, no symptoms were produced. This may have been due to the extreme slowness of absorption as compared with the rate of elimination from the circulation. Dr. J.F. Illingworth states, as the result of his observations while in the Fiji Islands, that the kava beverage, even when taken in large amounts, does not apparently affect the brain to an extent as to cause the drinker to appear as if under the influence of alcohol, but he appears as if the muscles from the hips downward are paralyzed. These symptoms last for about half an hour, at the end of which time the person is perfectly able to walk home. In general, the active constituent of any drug produces a more pronounced but more fugitive effect than the crude drug itself, and one might therefore expect more violent reactions from the isolated active constituents of the ava than from the crude infusion. Judging from the negative results obtained from the injection of the olive oil emulsion, it is probable that the physiological effects described above, following the intravenous injections of the various preparations, were not mechanical but must be ascribed to the action of the constituents of the ava. Conclusion. The crystalline product consists largely of methysticin, the methyl ester of methysticinic acid. In addition to this, there is about 5% of the free methysticinic acid present. The resinous product consists of about 5% of free resinous acids, which acids can be separated into 3 different acids or groups of acids according to their solubility in different alkalis. The remaining resinous product is composed of ester resins. On hydrolysis, these esters yield 3 distinct acids, 2 resinous acids and methysticinic acid. The 2 resinous acids are distinctly different, both in physical properties and in chemical properties. They can be sharply separated by means of the difference in solubility of their barium and iron salts. These acids may be separate individual substances or a group of related substances. The barium and iron acids, although different chemically, have some groups in common as shown by the formation of a common oxidation product. There are at least 3 alcohol radicals formed through hydrolysis, a resinous alcohol radical, a crystalline substance with a melting point of 130 degrees, and a volatile oil. The physiological action of the ava is due to the ester resins. The two resinous acids formed through the hydrolysis of these esters seem to be the two active constituents of the resin ester. From the above outlined work, it appears that the ava root does not contain any alkaloidal substance, as none of the constituents were found to contain nitrogen. That the aqueous infusion used by the ava drinkers contains the same constituents as are extracted by the ether is shown by the following. An infusion of the ava was made by allowing some of the powdered drug to remain in contact with water for about 12 hours. The infusion was then filtered and the filtrate extracted with ether. A resinous mass remained, which from all appearances was identical with the resins obtained from the ether extract. It also gave the same action when placed on the tongue as was produced by the resins from the ether extract. End of Section 7. End of The Chemical Constituents of the Active Principle of the Ava Root by Alice A. Ball.